Chapter D is a review of physics, and what we're going to do in D1 is look at translational kinematics. Now, kinematics describes motion and doesn't worry about forces. So we're going to look at a situation where we're going to be traveling in one dimension. Say this is the center of our town and there's a highway. And my car is going to start here. Call that x sub 0. This is the x direction. And we're going to consider the general case of constant linear acceleration, but we're going to build up to it. So this is motion in a straight line. That's what we mean by translational motion. And we're going to consider the simplest case is going to be one where there is constant position. Now, there is no velocity here. You're sitting in the car and the speedometer has 0. There's no velocity and there's no acceleration. So this is a case of constant acceleration. It's also constant velocity and constant position. You're going nowhere. Call that, say, 1. Now we'd like to make 3 graphs. 1 is going to be the graph where, as time goes on, we want to put down where the car is. So this vertical axis is your x, and your horizontal is your t. And then we want to plot the velocity as time goes on, and the acceleration as time goes on. Now, this is a very easy situation here because your acceleration is 0. The car is not even moving, so it's not accelerating. The velocity is 0. And the position, it's at x naught. It doesn't change. So these are your 3 graphs. Now there's equations that go with these graphs. We could say here x equals x naught. That's the equation. We could say here v equals 0. That's the equation. And we can say here a is equal to 0. There's no acceleration. And the next case we're going to consider is constant velocity. Now, velocity technically is speed and direction. Well, the direction is going to be along the x-axis here going, say, east. And the speed would be what your speedometer says. So the velocity is the speedometer reading and the designation that we're going east. And we would like to have the 3 graphs again. So here is time, and here is x. And here we have time, and we have the velocity. And here we have the acceleration and the time. Now, if it's constant velocity, so let's say that we started off a little bit before this position, but when the car is at that position, we're looking from the sky. We're looking down from the sky. And we see at t equals 0, the car is at x equals 0, but it's moving to the right at some velocity, which we will call velocity v sub naught. And it's not going to change. That's the initial velocity, and it stays the same. So when we start taking the data, car might be going, say, 60 kilometers an hour, 80 kilometers an hour, maybe 50 miles per hour or something like that. Whatever it is, that's going to be V naught. And since the speedometer doesn't change, the acceleration is once again 0. So the equation here, I'll put the equation underneath the graph, A is equal to 0. And here the velocity is a constant, V naught. And we're going to start out at x equal to x naught, like that in general. But now as we travel, as time goes on, we're going to be increasing our x. The x is going to increase in a linear fashion. And let me show you a neat little trick here. If we look at this rectangle, let's say that the speed here is something like 50 kilometers per hour. Then if we go, say, 4 hours, say this is 4 hours, then you would be going 200 kilometers as a distance. So if this here is a 50, this height, see, is a 50, that's along the velocity axis. And if this is your hours, if you multiply kilometers per hour by kilometers per hour, this height here is kilometers per hour. If you multiply that by hours, you get kilometers. So in other words, the area under the graph gives the distance traveled. So that means over here, we start out at x equal x naught. This is time here equal to 0. We can put a little 0 down there like that. All here, the origin. So this graph here is going to be x is equal to x naught plus the initial velocity, v naught, times t. So the x has two components. This component here is your initial x. That's where you start, x naught. And then this here is the distance you're going to travel in the time as t goes on. So this is going to be v naught t. So you can think of this as two pieces. X naught. If v naught is 0, then that's all you would have, this case here. But since v naught is not 0, we have this extra piece. Now, the nice thing about these equations is that this is more general. So if you let v naught equals 0, you then recover this one. And v naught equals 0, you recover that one. And the acceleration is 0 in both cases. So the area under the graph here of the velocity gives the distance traveled. Notice that the slope here, if you take this slope, the rise over the run, your rise is v naught t. And if I divide by the run, which is t, I get v naught. So this is giving me the slope function of this graph here. Isn't that very, very cool? All right, so we want to consider the more general case where we have constant acceleration. Well, you might say, well, we had constant acceleration in those two cases, but I mean now where the acceleration is not equal to 0. So we're doing a more general case. And now we can give the three graphs, say x and time, the velocity and time, and the acceleration and time. So here the acceleration is a constant, but it's not going to be 0, so it's going to be up here somewhere like this. Now, I would prefer to just call that A. Now, I know that that's the axis A, but we sometimes do that, you know, that we say that this is the T axis, but then any point in there can be an arbitrary T. So I'm going to just say that is A. And if you want, we could say the A axis like that, and then say put the A right there. So that's the acceleration. Now notice that here, some acceleration, not equal to 0, but it is constant. That if we look at this straight line to get this equation, this is very, very similar, because just like the velocity is a change of position with respect to time, the acceleration is a change of velocity with respect to time. So in other words, we start out here with some V naught. This graph is going to look similar to this one. Then we're going to come up here like this, and we can consider here that we're looking at two pieces. The piece here is your V naught, but then the additional piece here is your acceleration times the time. See, that's the area. We could say here, looking at the area under this graph, how about 1 kilometer per hour per second? So we would say per second, we would put that second down here, because when I have per, we put it in the denominator. So that means we would start off, say we might start off with 50 kilometers per hour, then in 1 second, you're going 51, and then 2 seconds, 52, and all like that. So the velocity equation then is your initial velocity plus your acceleration times the time. And see, it works out very nicely with the units, because the acceleration would be like 1 kilometer per hour per second. But then if you multiply by 4 seconds, then you would get 4 kilometers per hour. And then you would add that to what you started with. And we could say we started with some velocity V naught, say 50 kilometers per hour. So that would be then 54 kilometers per hour. Just think of the speedometer in a car going up an additional kilometer per hour every second. Or if you want to think in miles, if your car has miles, you may be going 50 miles per hour, but then every second you gain a mile per hour. Once again, the slope here is a constant, and this is the area that's represented here in this increase from our initial point. So we can find now the x by finding the area of this graph. Just like we did here, we found the area, and that gave us our equation. So what's the area of this? Well, this area would consist of two parts. We have an area here, which would be V naught T. V naught T, that's the area of that rectangle. Then we had the area of the triangle. Well, that would be 1/2 the height here of the triangle times the base, or altitude times the base. So that would be here, this distance here along the time axis, that's your T. And this length of that part of the triangle is AT. So you need 1/2 T times AT. So that's 1/2 AT squared. So now we're ready to come over here and say, well, you start out with some x naught, and then what we're going to do here, we can write down the general formula. It will be x naught, and then the distance traveled is given by the area here, so we have V naught T plus 1/2 AT squared, and that's a parabola. So that's going to do something like that. And these are kinematic equations, or kinematical equations, if you'd like to say kinematical. So you have here these three. Now moving to the right with these graphs, that is differential calculus, where you're plotting the slope of the previous graph. So differential calculus. And then when you go from the right to the left, you're going this way, like that. That's called integral calculus. Integral calculus. What you're doing is you're finding areas under the graphs. And when you do that, notice that when you go to the left like this, you pick up a constant, V naught, and here you pick up another constant, here X naught. And it's called a constant of integration, and it's set by your initial condition. When t is equal to 0, that's what that's going to be, X naught for your position. When t is equal to 0, you'll have initial velocity. And when the t is equal to 0, the acceleration is constant, so it's the same. Now, it would be nice to have two more equations. If you look at the equations we have so far, let's look at our parameters. We have x, v, and a, and a t. So we have v, x, v, a, and t. This equation here has no v. Now the v naught and x naught are constants, they're initial conditions. So we're basically looking at the variables here, x, v, a, and t. This has no v. This one here has no x. It'd be nice to find two more, one that has no t, and one that has no a. All right, so there's no x, no v, no a, no t. Well, I can find the one with no a by looking at the area here, and instead of dividing it up into two parts where you have a triangle and a rectangle, I'm going to look at this as a trapezoid where I have a V naught here. This is my V and this is my T. I'm pulling this one down here. And then at the far right here, notice that that's your V, because V naught plus AT, that's your V. So this is V to go up to here. And this is V naught. And go ahead and do it like that. That's V naught. And this is T. So the area of a trapezoid is you would take 1/2 the heights. You would take an average of the heights, say V naught plus V, and then multiply it by the base. So that has to also be your X. Well, you have the initial X naught. So we would say that X is equal to X naught plus this distance traveled due to your acceleration. So here it is, V naught plus V times T. So that's another equation, and that has no A. Well, what about one with no T? Now, I like to write this one with X minus X naught as the distance traveled. That kind of simplifies it a little bit notation-wise for me. All right, so I'm going to do that like this, the distance traveled. And you always could put in the X minus X naught for the D. So now what we're going to do is we're going to go to this equation up in here. V equals V naught plus AT And since we're looking for one now that has no t, we need to eliminate the t, this t. So t is, from this equation, v minus v naught divided by a. All right, this equation gives us this one. Then I'm going to put this one in here to get rid of the t. So that would give me d is 1/2. Now I'm going to write the v first here and the v naught second. And then here I have v minus v naught over a. And now remember from algebra that I have like a plus b times a minus b, I get a squared minus b squared. So this is going to be 1 over 2a v squared minus v naught squared. And that's my fourth equation, one that has no t in it. So now I can put this back as x is equal to x naught. Well, this is actually x minus x naught. So I can then bring the x naught to the other side of the equation and have then plus 1 over 2a. But you know, I don't like this form. I really like this d. So I would take this 2a and hit it with that d and wind up with 2ad. I like this. It's easy to remember. V squared minus v naught squared. This one here. And, you know, if you disagree with me, you could always put back for the d x minus x naught, but you would put it in here then. You would put it in here because this looks kind of nice. There's like no denominators. I think that's clean. So there you have it. No t for that one. And if we go to this one here, we have no a. So you could subtract that x naught and put it d equals that if you'd like. And then here, if we go to our original 2, this one had no v, and this one had no x. So now we're covered. We have all 4 cases.